And the first talk is by Ju Wang. He is a postdoc at the University of Waterloo. He works with Professor Omida Bari and Keshav in the RF-based sensing area. His research includes Internet of Things, mobile systems, and wireless networks. And today he has a very exciting talk on how to hack RFIDs for fun and profit. So, Ju, take it.
Hello, everyone. I'm Zhu Wang from University of Waterloo. This is a joint work with my colleague Amita and Keshav. Okay, sorry. Oh, sorry. Okay. There are lots of interest in the battery-free and low-cost sensors for the temperature sensing, light sensing, and so on. However, when you look at the existing market, the RFIDs are battery-free and also it's no cost, but they cannot sensing. Well, the WISP is battery-free and also can sensing. However, it is not no cost. So ideally, we want to find a device that is first battery-free, second no cost, and lastly, the most important, can do the sensing. So the question here is that how can we build such a device, the battery-free and low-cost sensor? So to build such a sensor, usually you need the knowledge of electronic. Then you need to design the PCBs, and finally, you need to spend a lot of money for fabrication. Unfortunately, the process is costly and time-consuming. So in this talk, I will show you how even a high school student can build a battery-free and low-cost sensors by hacking the RFIDs. This is a RFID tag. It is a cheap and low-cost RF reflector with a unique ID. To read this tag, you need an RFID reader. The reader transmits high-pass signal. The tag has low battery, so it's just a reflection or line reflection to the reader. For example, the reflection means for the 1 bit, and the line reflection means for the 0 bit. Okay, now that I have explained the RFID tool, let me show you how we convert this RFID tag to a light sensor with a pair of scissors and a photoresistor. It only has 3 steps. The step 1, removing the plastic cover. We remove as you can see now, the plastic cover is removed, and we can see the test antenna clearly. The step 2 is cutting the test antenna. We use scissors to cut off a small part of this tag. Looks like this. And step 3, we need to place a sensor on this tag. For example, we place a photoresistor on this RFID tag to replace the cut off part of the tag's antenna. Now, you get a battery-free and low-cost light sensor. As you can see that the whole process is so simple that even a high school student can do it. But let me show you how even this simple idea can work in reality. Look at this modified RFID tag with a photoresistor. The resistance of this photoresistor will change over the light intensity. For example, when the light intensity goes up, the resistance will go down. So let's consider 2 simple cases. The case 1, the light is off. Then the resistance of this photoresistor is large. Note that now the photoresistor is a part of the test antenna. So in this case, the impedance of the test antenna is large. As a result, when the reader queries this tag, the tag will reply a weak signal. Well, in case 2, when the light is on, the resistance of the photoresistor is small, so the impedance of this test antenna is also small. So when the reader queries this tag, the tag will reply a strong signal. So that is to say we can estimate the light intensities by simply detecting the power changes of the test reply signal. The idea is so simple. However, it is non-trivial to realize it in reality due to the environment changes. For example, here, when the light is on and the tag will reply a strong signal. But when a human body, like me, draws the direct path between the reader and the tag, the strong signal will become a weak signal. So this weak signal will give you a wrong estimation. Since the weak signal means that the light is off, which is not true here. To better understand the challenge, I will show you some results. In a dynamic environment, we fix the light intensity and we check the distributions of the received signal strength, RSS, of the modified RFID tag. As we can see, even the light intensity is fixed, the variations of the RSS variations of this modified RFID tag is very large, up to 15 dB. So the challenge here is that the RSS changes not only by the light intensity, but also by the environment. We need to remove the environment impact before we can get an accurate estimation. So how can we solve this challenge? Our solution is the differential sensing. Specifically, we deploy a reference tag to this modifier tag. We do not do any modification for the reference tag. When the reader queries this tool tag, the tool tag will reply to the reader at almost the same time. As the reader said, the received signal strength of the reference tag is only related to the environment. Because we do not do any modification for the reference tag, well, the received signal strength of the modifier tag is a function of both the light intensity and the environment. With differential sensing, we want to say that the differences between these two RSS measurements is only related to the light intensity. The key intuition here is that these two RFID tags are deployed so close so that they will suffer from almost the same environment impact. So it is likely the environmental impact will be cancelled out with the differential sensing. So let's check if the differential sensing can help us to reduce the environmental impact. This is the absolute RSS of the modified RFID tag I have already shown you in the previous slides. Let's compare it with the differential RSS. As we can see, the differential RSS, the variation of the differential RSS is much smaller than the absolute RSS. So it implies that our differential sensing method can indeed reduce the environmental impact. But even with the differential sensing, the variation of the differential RSS is still unstable. For example, with a 90% variations that are less than 6 dB. So what can we do now? Our solution is the minimum response threshold, namely MRT. Let me first show you what's the MRT. Recall that when a reader wants to communicate with this tag, the reader will transmit a high power signal to activate this tag. So let's consider a simple process. Well, the reader increases its transmission power from low to high, and we check if the tag has response. When the reader's transmission power is low, the tag has low response. Well, when the reader's transmission power is higher than a threshold, the tag becomes response. So we call such a threshold as a minimum response threshold. In other words, the MRT is a required minimum transmission power of a reader to active an RFID tag. We also found that when the light intensity changes, the MRT also changes over the light intensity. So we use a differential MRT for the temperature sensing, light sensing, instead of the differential RSS. But let me show you if the differential MRT is better, it's more robust than the differential RSS. This is RSS and the differential RSS I have already shown you in the previous slides. We compare them with the differential MRT. Under the same environment and experiment setup, we collect the data for the differential MRT. As we can see, the differential MRT is very stable, with a 90% variations that smaller than the 2.5 dB. So in this paper, we use the differential MRT for the light sensing, temperature sensing. Okay, now let me show you the applications and the results. The first application is the temperature sensing. A thermistor is used to modify this RFID tag to build our temperature sensor. We change the temperature by using a heat gun. We measure ground truth temperature by using a thermometer. We change the temperatures from 2 to 70 centigrades. In this figure, the SS is a temperature and the YSS is a differential MRT, which is measured at the read side. From the results, we can see that with the increases of the temperature, the differential MRT decreases constantly. That is nice, because we can use a differential MRT to estimate the temperature. So the second application is light sensing. We use a phototransistor to modify this RFID tag to build our light sensor. And we change the light intensities by moving the light source far away from the light sensor or close to the light sensor. And a light meter is used to get the ground truth. We change the light intensities from 0 to 300 lux, which is a normal indoor light intensities in most indoor environment. In this figure, the SS is a light intensity and the YSS is a differential MRT, which is measured at the read side. Again, with the increases of the light intensity, the differential MRT decreases constantly. So we can use the differential MRT to estimate the light intensity. Lastly, I will show you a battery-free and low-cost keypad. We built this keypad with 4 RFID tags and 4 switches. When you press one switches of one RFID tag, this switch will connect the test antenna to the test chip. So the reader can read this tag and identify which switch is pressed. This keypad can be used for many remote controls for the IoT applications. Okay, beyond all the 3 applications I have already introduced at here, there are many other applications that are enabled by our approach. For example, the humidity sensing and the pressure sensing and so on. Well, our work is not without limitations. So I will discuss the limitations and the corresponding challenges. The first challenge is how to improve the sensing range. For an unmodified RFID tag, the working range is up to 10 meters. However, after modification, the range is only reduced to within 5 meters. To improve the sensing range, you need to make sure the impedance matching between the test antenna and the sensor. The second challenge is how to improve the sensing accuracy. We first need to improve the resolution of the differential MRT. Our reader can only provide our reader can change the power only within a step of half dB. So one may improve the resolution by using a good reader. Second, we need to identify a good sensor that can detune the test antenna constantly. And third, design a low-cost RFID reader still is an open challenge. We also pointed out other challenges in our paper, so for more details, please refer to our paper. Okay, now let me conclude this talk. First, we introduce a new method that design the battery-free and low-cost sensors by hacking the RFIDs. Second, we introduce a new sensing feature called differential MRT, which is robust to the changes in the environment.
Okay, let's thank the speaker again. Really cool idea. So our next speaker is Ming Jin. She is currently a postdoc fellow from Tsinghua University. Her research interests include backscatter communication, wireless coexistence, and clock synchronization. And today she has a very exciting talk about parallel backscatter in the wild when burstiness and randomness play with you. So let's listen.
Hello everyone, I'm Meng Jin from Tsinghua University. And today I'm going to share with you our recent work about parallel backscatter. As the backscatter technology gets proliferated in the areas like warehouse and manufacture, so the deployment scope and the scale of the backscatter device have extensively increased in recent years. So indeed, not only the number of tags have increased, the volume of data that's transmitted by each tag is also increased due to the increased sensing capabilities of the tags. Therefore, how to fully utilize the channel and enhance the network throughput turns to be a very important problem. To solve this problem, parallel transmission is explored in many recent works. They allow the tags to transmit in parallel, and the collision will be decoded at the reader side. To achieve this version, we need a parallel decoding method to decode the collided signal. So before talking about parallel decoding, let's first look at the signal when only one tag is transmitting. Since the tags will encode its data by reflecting or absorbing the camera wave, there are two magnitudes in the time domain, and we can use a threshold to decode the signal. If we look at the acute plan, we can see two sample clusters representing the two backscatter states. And now we have two tags. Since each tag will have two states, so we will have 4 states in total. And this state represents the combined state of the two tags. So now if we can map the four states to the 4 signal clusters, then the collision will be decoded. But how can we do it? Some existing work will leverage the location of the clusters as a feature to identify the state of the clusters. And some other works will do it by observing the signal's transition probability between different clusters. But indeed, all of these existing parallel decoding methods face a common problem, that is the superclustering problem. We can say that in this figure, signals from different states will overlap with each other. So in this case, we cannot even figure out how many clusters there are, not to mention identifying the state of the clusters. Indeed, superclustering is a very common problem, especially in parallel transmission scenario. Many reasons can cause such a problem. And the first factor is the low SNR of the tag signal. Indeed, the distance between the clusters indicates the strength of the tag signal. So for example, in this case, we show the collision signal of 3 tags. and all the tags are located only 1 feet away from the reader. And we can see that the clusters are separated with each other, since the SNR of all the text signal is very high. However, when we move one of the tags further away from the reader, we can see that some clusters become closer to each other or even overlap with each other, like this. Then when we move all the tags further away from the reader, like this, almost every cluster is merged into a supercluster. So in this case, none of the signal's combined state can be easily extracted from the IQ domain information. So I know you may think that this is just a real case, but actually no. As we know, the SNR for the typical backscatter communication will decay with the force power of the distance for the backscatter link. That is to say, the result that's harmed by the existing parallel decoding method is achievable only when all the tags are located very close to the reader. Otherwise, the superclustering problem will occur. So indeed, weak signal is not the only cause of the superclustering problem. Even the signal from all the tags are very strong. The clusters can still overlap with each other like this. And such a phenomenon becomes more serious when more tags transmit concurrently. So such a serious overlapping problem will of course lead to very poor decoding performance. Then we conduct experiments to evaluate the performance of existing parallel decoding method. So in the experiment, the reader is located at the center, and the tags are moved further and further away from the reader. This is the result of the experiment when 2 and 5 tags transmit concurrently. And we can see that the existing parallel decoding method works only for a very small distance, especially when more tags transmit concurrently. So in this work, we try to fill such a gap and propose a very reliable decoding method to support parallel backscatter in the web. So to achieve this version, the key is to separate the overlapped clusters. It seems that we can use the density of the signal samples. Then the center of the clusters can be identified by finding the density peaks. It sounds simple, right? But actually no. These two figures show the supercluster that's composed of 2 clusters and 4 clusters, and we can see that indeed the overlapping area have higher density than the center area. This is because that the overlapping area will gather the outlier signal samples from multiple clusters. So only utilizing the IQ domain information is no longer effective here. So in this work, we add a new dimension, that is the time domain. We can see that since the reader can oversample the received signal, the signal will dwell on a cluster for a certain period of time before it flips to another cluster. This is called the temporal burstness of the signal. And then if we look at the signal's movement in only one cluster, we find that the movement of the signal follows a Gaussian process. So we term this behavior of the signal as the bursty Gaussian behavior. So in this case, if we can extract the signal from the center area and the overlapping area and observe the arriving time of a sample in these 2 areas, we can find that although these 2 areas have very similar densities, the arrival of the signal samples in these 2 areas have very different distribution. Indeed, the samples arriving in the center area will show higher burstness. This is because the samples may occur in this area only when the signal deviates on the corresponding state. So in this case, if we want to find the center areas, we can search the IQ plane with a moving grid. And for each location of the grid, we can calculate two metrics. The first is the density, and the second is the burstness. Here, the burstness is quantified by chi-square test. And we can see that here only the center area have both high density and high burstness. So now we have found the cluster centers, and the next target is to identify the state of the samples. The challenge we face here is how to identify the samples that are located at the overlapping area. Our idea here is to using the signal transition patterns. In fact, the longer the signal has state on a certain cluster, the higher the probability that the signal will will flip to another cluster. So, for example, in this case, the sample S1 located at the overlapping area of cluster A and cluster B, and we don't know which cluster it belongs to. But when we look at the transition law of the signal, we find that signal's average deviate time on a certain cluster is 25 samples. And we also find that when sample S1 arrives, the signal has stayed at cluster A for only 6 samples. So this indicates a very low transition probability. And then let's look at another sample, sample S2. It also located at the overlapping area. But we find that when S2 arrives, the signal has stayed at cluster A for 28 samples. This indicates a very high flipping probability. So we can infer that sample S1 maybe belongs to cluster A, and S2 may have already flipped to cluster B. So based on the above analysis, we designed a Markov-based model to identify the state of each sample based on both the signal's location on the IQ domain and the signal's transition pattern between different clusters. Then let's look at the performance. We implemented Hubble on USRP N210 software-defined radio, and we used this radar to read the programmable text. And we compare Hubble with two methods. The first is backgraph, which combines the time and IQ domain information to identify the clusters. And the second is flip tracer, which identifies the clusters based on the signal transition pattern between different clusters. Our goal here is to evaluate the performance of Hubble under different number of concurrent attacks and under different SNR. In the experiment, we changed the number of tags from 1 to 6. And during each round of the experiment, we move some of the tags further and further away from the radar, and this will change the SNR of the tags. So this figure shows the throughput efficiency of Hubble and the flip tracer when there are four tags transmitted concurrently. Here the x-axis shows the SNR of the distant tags, and the y-axis shows the number of the distant tags. We can observe that for flip tracer, moving only one tag further away from the radar can cause serious of performance degradation. And in comparison, Hubble is much more robust in the low SNR scenario. Indeed, Hubble shows decent performance even when all the tags are moved further away from the radar. And this figure shows the performance of the three methods when different number of tags transmit concurrently. And indeed, for all the three methods, the performance will decrease when the number of tags is increased. However, compared with flip tracer and the backgroup, Hubble is not so sensitive to the number of tags due to its ability to trace signal transitions even when the signal is highly jumbled. So this figure shows the CDF, the throughput of Hubble, flip tracer, and the backgroup. And Hubble has a media throughput efficiency of about 0.82. It outperforms flip tracer and the backgroup by about 11 times and 7 times respectively. And we further conduct experiments to evaluate the performance of Hubble in non-line of sight scenarios. In the experiment, we change the number of tags from 2 to 4, and some of the tags are non-line of sight tags. And these three figures shows the performance of the three methods under different number of concurrent tags. And we can see that the influence of non-line of sight transmission is more obvious when there are more tags transmit concurrently. And compared with Hubble, the existing methods are much more sensitive to the non-line of sight scenario. That is to say, Hubble is more applicable for the highly cluttered environments such as warehouses, stores, and factories. So in conclusion, we disclose the superclustering phenomenon which exists in almost all the parallel backscatter scenarios. And in the process of exploring the root cause of the superclustering phenomenon, we find that the spatial temporal distribution of the created signal follows the Birthday Gaussian behavior. And based on this observation, we propose Hubble, which is the practical effort to achieve highly reliable parallel decoding in the low SNR scenario. At last, Hubble is implemented on a USRP N210 software-defined radio, and it's evaluated through experiments conducted in different environments. So thank you so much for your attention.
So our next speaker is An Long. He's currently a postdoc at Carnegie Mellon. And he is on the market this year, so he's looking for a job. He'll be talking about radio frequency sensing, and they've done a lot of experiments, and they're going to share their experience with us. And before that, he was a graduate at University of Utah.
Thank you for the introduction. And again, this work was done with Pete and I while I was still at the University of Utah. Since then, we both have graduated. So let's talk a little bit about why we actually did the work in the first place. One of the main reasons was there was a conversation with the doctor and physicians, and they are motivated by, is there a way to actually monitor the patient in-home for in-home elder care as well as opioid epidemic. So what they actually want to know is the patient's breathing becomes abnormal at any point in time. As you can see in this photo, on the right, I put half of the sensor that they actually put on the patients. It becomes it's very uncomfortable, and it's very wieldy, error prone. So with the rise of the IoTs, we flood the motor home with lots of radios, a lot of sensor. We kind of ask ourselves, wait a minute, if there's all of these sensors that's already inside the home, can we use them in order to detect breathing? So one of the other works that's already in a lot of previous works, we see that there are tons of different ways to do breathing monitoring with radio channels information. But at this moment, it's kind of hard to tell the doctor, hey, this is the right technology to move forward and use. One of the reasons for that is none of these have actually shown in a medical study that it's actually going to work, right? Most of these are actually done in very controlled experiments, either in an anechoic chamber or some kind of laboratory experiments. We're starting to see that there is a couple of the newer study that started to do some kind of in-home kind of study, but it's very limited, and the amount of data that it's introducing is not enough. So there's still a couple of things that are still very unclear to us. Is how does the bandwidth actually affect the performance? Second is, how do these different types of motion removal impact the performance? And third of all is, how are these commercially available RF technologies compared to one another? And do they actually perform in a long-term study? So in order to do the comparison, we designed a very extensive side-by-side study. And we have found that in the nearby sleep-wake center, they're doing a lot of these kind of sleep study, as you saw earlier in the picture. Is the reason why they're actually doing the sleep study is they want to be able to figure out why a particular patient having trouble breathing after changing drugs, or if they are just chronics. So we've worked with them. We worked with 20 different, we gathered data from 20 different patients, over 160 hours of data. And the ground truth is actually a video feed that's annotated by a professional. And in the annotation, they basically figure out when's the motion, if there's any motion, and if there's any of these abnormal breathing. So we've done some of our preliminary analysis on the data. We'll present it a little bit later on. But one of the key things that we want to convey in this paper is we have a data set that we found that it doesn't actually work very well with the conventional processing techniques, and we want your help in order to make it a lot better. So without further ado, this is the link to the data. So far, we have 305 downloads as of October 25th. So my hope is by the end of this, we'll have hundreds more. So you may ask, hey, An, what is actually inside a data set? What do you actually capture? And here is what's inside the room that's capturing the radio frequency. We select most of these radios and technology based on the current state of the art, as well as doing selective picking of channels, bandwidth, in order to not interfere with one another. So as you can see, we have sub-gigahertz radio for 915 megahertz. We have 2.4 gigahertz radio that's basically Zigbee radio. We have the ultra-wideband with the decawave that's doing 500 megahertz of bandwidth. And we also have the most popular one, which is the Atheros CSI. And this is doing the 2x2 MIMO with both 2.4 and 5 gigahertz that have 114 subcarriers. So now that we have these sensors inside a box, how do we actually set up the experiments? So on the left is a picture of one of these, like a diagram of one of these sleep center room. And on the right is the hardware that we actually use in order to do the experiments. So one of the key point here is inside the box, if you notice, we're using a lot of directional antenna. And one of the things that we figure out early on is RF tends to bleed. And these sleep center have rooms that are like very close to one another. So a person that's in the room over will affect the experiments in this room. So since we don't really want to have a kind of unknown variable, we decided that it's best to just do directional antenna and just constrain the area of influence. So one of the thing about medical study is the ground truth is extremely important. One of the ways that we actually do ground truth was we actually use the medical devices that the professionals are currently using. And that's including the chest, the abdomen sensor, the nasal, the thermal sensor that they are currently using. There's a lot more data than just these four. The only problem is some of them doesn't actually work very well, and some of them might just show repetitive data that's not very useful. One of the other issue is, if you notice, the black line is the raw signal that you actually get out of the sensor. They're quite noisy, depends on how the person is laying or how they're breathing, or depends on the person. So we decided to do a little bit of a cleanup ourselves, did a little pre-processing, did a little filtering, and the red line is what you actually see at the end, which is a lot easier to process as the ground truth. More details are in the paper, so if you really want to know, like, does the pre-processing and the filtering, does that actually bias the experiment at all, you can go back and check that. So now come to the more interesting parts, is we collected data for CSI, we collected CAR, so channel state information, channel impulse response from Decawave. We also capture RSSI from Zigbee. This is 1 dB step size. And we also use a technique that I presented in Hot Wireless in 2016. I simply just call it sub-dB, because with this technique, you can see that I was able to get 0.013 dB of resolution rather than just the 1 dB. And you can see that the signal is slightly better on the lower right. Again, we apply a little bit of filtering, pre-processing in order to get the red signal. And as you see, in all four of these cases, you can actually visually see that there's actually a breathing signal in there. So since each of these have their own little pre-processing, we decided, well, it's best to just abstract that away rather than include it into the entire processing chain. We also did some sort of filtering as well as computing the respiratory rate. So this is one of the results, is we decided to compute the breathing rate for all 20 patients over 160 hours. And as you can see, CSI tend to achieve 2 to 5 times better median respiratory rate estimation over all the other technology. One of the reasons for that is we think is because of the amount of channels that Wi-Fi are able to give. Notice all the other technology only have 1 to 2 channel or 16 channel at most. So you don't have that many channel selection to choose from, channel diversity to choose from. Also, one other thing that makes the error so high is because of the motion. As soon as the patient moves, you need to know when they move or how they move in order to remove the data from there. So as you can see in the graph, the gray line is showing exactly when the patient actually moved. As you can see, the respiratory rate just right before that was pretty good. As soon as the motion happened, it becomes pretty hard to predict. And since it's hard to predict, it's become very unreliable. So you can actually, in most of these papers, it shows that you can actually remove the motion by doing different techniques. Here we're showing 5 different techniques that are currently in use right now. One of the key takeaways from this is the more motion you remove from the data, the better the respiratory rate estimation becomes. But note that especially for the green on the bottom right, you're removing more than 40% of data out of the overall experiments. And through the ground truth that we actually saw in the experiments, we expected the motion to be less than about 10%. So if we have a really good motion detection algorithm, we should be performing at the 10 mark of the x-axis. So the second reason why breathing estimation is hard is because of as I was saying earlier, is because of the unfavorable fading that happened in the channel. So when we do experiments with, for example, RSSI with 16 channel, we see that 4 of the 16 channel actually show some sort of breathing rate. The other 12 channels doesn't actually show. It's because of depends on how the person is laying or how how the environment was set up. You might have a destructive interference that caused the breathing rate to be so much below the noise floor that you can't even detect it at all. So what I'm showing here is on the top, these are motion events, right? Before the motion events, you can see that the estimation is well within 0.25 ppm. Breath per minute of the truth. As soon as the patient move, shown by the second line, they go into this other unfavorable fading that basically caused the error to shoot up to more than 0.2 breath per minute. But as soon as they turn back into the original position, you can see that the results come back down to 0.2 breath per minute. So one of the key takeaway here is not only motion detection, but also channel selection. So the more channels you have, the better chance you're going to have at selecting the right channel to actually see breathing. So we kind of answer one of the questions that we posed earlier is, does the bandwidth actually affect anything? And the answer is yes. If you have enough channels, you're going to improve the performance of the breathing estimation. That's it for me.
So our last speaker for this session is Jai Zhao. He is a PhD student from Simon Fraser University. His supervisor is Professor Jai-Chon Lee, who leads the Net Media group at Simon Fraser University. His talk is going to be about multi-hop backscatter on commodity Wi-Fi. So most backscatter papers we've seen so far have always been single hop, and he's going to tell us about multi-hop once he's ready.
So hi everyone, I'd like to talk about our work extended toward multi-hop backscatter communication with commodity Wi-Fi. This is a joint work with Dr. Wei Gong and Professor Jiangchuan Liu. Backscatter validates that sensor communication can work without any power-hungry transceivers. Backscatter uses RF signal reflection to transmit data, and in a backscatter system, tag convey information by changing its antenna's impedance, deciding whether to reflect the excitation signals or not. An external radar generates the excitation signal and decode the tag information. Since sensor data transmission plays an important role in a lot of applications such as robot sensing, indoor localization, and embodied sensor data exchange. These applications need low power or even zero power connection solutions. So backscatter can be a good choice. A frequently asked question is about the relation between backscatter and other connection solutions. We believe that backscatter is not designed to replace other wireless technologies, but designed to make communication things easy and efficient. This is just like we see things by the reflection of sunlight. It's natural and easy, but we also need TV, telescope, radar, and satellite to see things far from us. When we use backscatter in more and more complicated applications, we want more than just energy efficiency. We thought that path diversity may also be important. We see a lot of examples from traditional network design, such as the data path adaptation in wireless sensor networks and multipath transmission in data center networks. They enhance the network utilization, robustness, and scalability. So we ask the question, can backscatter communication also benefit from path diversity? If we look at the single hop backscatter, it may experience unreliable channels, especially when the densely deployed tags have physical obstacles, such as moving humans, walls, and indoor facilities. This robustness challenge can actually be tackled from building multi-hop backscatter. And the key is that backscatter tags can do relay for each other. If we can achieve this, we can not only provide backup paths to deal with the obstacles and poor channel conditions in a single hop case, but also promisingly lead to even multipath transmission for backscatter communication. We want even more than tag relay. Since our multi-hop backscatter model follows a route from the excitation to tag 1, to tag 2, to tag n, and finally to the receiver, each tag has its own sensing data, and the tags should not only work as relay for each other, but also embed their sensing data together in a single excitation packet. So we can decode all the tags information at the same time with commercial radios. There are several challenges. The first one is interference. Our multi-hop backscatter model will generate a series of intermediate backscatter signal. These signals all spread in Wi-Fi band, and if we want to use commercial Wi-Fi devices to decode all these signals, we have to deal with not only the interference between the excitation and the backscatter signals, but also the interference among multi-hop signals. And second is that we need extra control operations, such as assigning a route synchronized with the excitation packet data and having multiple text information in one single packet. And we also have to consider the inverse routing. Multi-hop tags would generate the out-of-order backscatter packet, and this will impact the bit error rate when we decode the tag data. We deal with these issues one by one. First, we use a multiple frequency shift to cancel the interference. This is an analog way. The excitation signal is reflected multiple times, and for each time, there is a frequency shift using an RF switch. And from this frequency spectrum of the two-hop case, you can see that each hop can avoid being affected by its previous hop. And second, we allocate data fields for multiple tags. This includes a series of operations such as detect the packet duration, separate the data fields, and use control signals to set the order for multi-hop tags. And for the third one, we did measurement and found that the out-of-order reflection have much lower signal strength than the in-order reflection. So we can set a threshold in the decoding to eliminate the out-of-order backscattered packet. Following these solutions, we built a multi-hop tag prototype and a Wi-Fi energy harvester. Its front-end analog circuits not only detect the Wi-Fi excitation signal, but also filter noise and transform the detected signal into available voltage for the FPGA. Then a part of FPGA circuit is designed to read the control signals and perform the data fields allocation. Another part of FPGA circuit is for the tag modulation. We use Xilinx FPGA's IP core, digital clock manager, to generate both 25 megahertz and 50 megahertz clock signals. When the tag relay is turned off, each tag uses a 50 megahertz clock signal. And when the tag relay is turned on, each tag uses a 25 megahertz clock signal. And we use phase change to modulate the tag data and ensure that the IQ data after tag modulation still falls in the same constellation, so that we can use any commercial Wi-Fi devices to decode the tag data. We use a digital counter to synchronize with OFDM symbols with tag information, and following the order of multi-hop tags, we also synchronize tags data with its allocated range in the data field. In this experiment, we first evaluate the signal strength. We use 3 different types of Wi-Fi excitation signals, and we can see that the backscatter signal strength decrease with the distance between the tag and the Wi-Fi receiver. At 8 meters, the signal strength decreased to minus 85 dBm for all the 3 cases. The throughput also shows a general downward trend over the distance. We achieved 2-hop throughput up to 200 bits per second for the 11B signal. This figure shows the bit error rate of the decoded tag data, and the BER values generally increased with the distance between the tag and the Wi-Fi receiver. And when the distance is less than 50 centimeters, the BER value is less than 10%. We also examine how the performance changed with the distance between how the performance changed with the tag-to-tag distance, and the CDF figure shows that the tag-to-tag distance increased from 5 centimeters to 40 centimeters, and the signal strength decreased from more than minus 70 dBm to less than minus 80 dBm. The signal strength decreased fast from 5 centimeters to 10 centimeters. The other two figures shows that there is a degradation of throughput and BR performance when the tag-to-tag distance increase. Our current implementation of multi-hop tags also have limitations. Since we use the analog way to reflect the excitation signal multiple times, the signal strength will attenuate fast and directly impact the throughput and the communication range. A possible solution is to use a digital way to first decode the intermediate backscattered signal. But we also have to care about the synchronization issues because we want to decode all the text information at the same time. So there is a trade-off. We also have to add more flexibilities of the channel selection and routing configurations in our further work. To conclude, we have built a multi-hop backscatter system and demonstrate that backscatter tags can do really for each other and send their sensing data simultaneously and work with commercial radios. We hope this is a step towards more efficient IoT sensor networks. That's the end of my presentation. Thank you.